Fabio delsordo, title on the generation of vorticity.
Good morning, everybody. Thanks to organizing for giving the possibility to be here. I will briefly present a work I've been doing together with Axel last month. It is actually accepted for publication a few days ago. And this is a study, a numerical study on generation of vorticity. That is more or less, as you can see here, these three pictures. A phenomenon that is kind of common in it's a phenomenon that we can observe more or less wherever everybody knows here in the audience. And but we are interested in studying vorticity in the context of an interstellar medium. So the context is the study of the interstellar turbulence, and so in this sense, our setup is it makes sense to study a system with an irrotational flow. That means that in our setup, basically we have a box, and we simulate with pencil code, of course, explosion. So in simulating as a spherical expansion. Indeed, in the generation of vorticity due to spherical expansion, it is known from literature that in the isothermal fluids we can observe only numerical vorticity. If we have an isothermal case, some vorticity is observed, as shown in this work of Axel Brandenburg and of 2006. But if we remove the isothermal condition, that means that we can study a barotropic case, baroclinic case. We see that the production of vorticity increase. And this has been studied also by Marie Corbett and other people. And so we studied this is the equation of evolution of vorticity, in which we have these two terms that are due to viscosity, and one is just due to the stress tensor, and the other one is the one that is actually that appears in the equation for the evolution of vorticity in the part that is very close to that's the same form of the induction equation. So, a quick description of the setup. This is actually taken from previous work that I already mentioned. And so we have a box, and we have a spherical expansion that are driven randomly. And then here you can see that the evolution of the box, at some point everything is turbulent. So we take a time scale in which we can study the vorticity before that everything starts to be turbulent. We study weakly supersonic flow because otherwise we are not able, or anyway we have more problem in solving shocks. We have periodic boundary conditions, and we study the ideal gas case. So we put the potential forcing, that is a Gaussian potential forcing, and of course we have this. Our system is described by these two equations, in which here in the momentum equation you can observe that there are three different effects. That is, one due to the shear, the other one due to the rotation of the system, the other one due to the fact that we are not an isothermal case. So we can observe something to the thermodynamic, some production of vorticity due to the thermodynamics of the system. So we go to, what we've done is study these three different cases separately. So first we put rotation in the system, but we are in the isothermal case, so barotropic case. And here these plots summarize our results. We have two different kinds of forcing, basically, One is delta correlated, so the southern number is 0. And the other kind of forcing is delta correlated, so there is a finite time in which the forcing is up. And here we can see that in this case, so here we show correlated number versus k omega over kf, in which k omega is a quantity that quantifies the production of vorticity. In this case, we see, for example, that the vorticity is increasing, going to big correlated number. So, of course, when we increase the rotation. While, for example, in these other cases, when there is a delta correlated forcing, we see that there are some differences due to different resolution and different Reynolds number. And here, so we can say that this vorticity that is observed here is due to some numerical effect. And this is actually a very important thing to point out, because, of course, we can, since we have a finite resolution, we can observe the numerical vorticity, and we want to understand what is genuine vorticity and what is real vorticity that is generated by physical effects. Indeed, here we can see that there is production of vorticity in this plot, in which we show the entropy and the kinetic energy. Because here we are showing this entropy for a different Coriolis number. And for example, here for small scales, we see that more or less independent, does not depend on the Coriolis number, the amount of vorticity that we have, the amount of entropy. And actually, we have that for very small scales, for more Coriolis number, there is more, the entropy, value of entropy is bigger, is larger. So this means that here there is some numerical effect that is taking place. While here, everything seems to be smooth. We remove from our system rotation and we put shear. And actually the form of the equation is rather similar, because this is the term that we have now, the evolution of the vorticity. And here also there is basically a similar effect, because going to very small value for the shear number, we have that there is some vorticity. So we don't go to zero vorticity generation. But at some point there is a strong increase of vorticity. And yeah, here also we see that there is something different depending on the forcing. But basically, this effect of the spurious vorticity for small shear numbers are observed. But most interesting case is the one in which we add this baroclinic term. So we remove isothermal condition. We also remove shear, so we have just a system that is evolving and without any isothermal condition. And here we have a two-dimensional simulation that shows what is the evolution of this quantity, temperature and entropy, and baroclinic term and vorticity in time. So here we see that the explosion is generated. And here there is another explosion that is taking place, and here the system is well evolved. And the baroclinic term basically is concentrated where the shock fronts are merging here. And indeed, also the vorticity is generated in the same part, and we see that at a later time, here vorticity is concentrated where shock fronts are merging. Also, the amount of vorticity in this case is rather larger than the previous case. And also we can see that in this case the problem of the spurious vorticity is kind of solved. And indeed in this plot we show that always kinetic energy and entropy. And we see that for small scales everything is going more or less the same way, depending on the forcing that is quantified by this field zero. This is the amplitude of the Gaussian forcing that I showed at the beginning. So independently for this forcing, we have that everything goes to more or less 0 here, while on large scale, so entropy is concentrated on a large scale. And we have to point out that the K, the K on which the forcing is acting is more efficient, more or less here. So this is the scale of injection of energy. And then there is some sense transportation of entropy on small scales, but also on large scales here. What do we learn? We are interested in studying this in context of galaxies, but in context of galaxies we have the correlative number and as well as shear number are very small. So rotation and shear may not be able to produce sufficient level of vorticity in galaxies. And so our conclusions are that Barocklinian term is the main cause for the vorticity in galaxies, at least when we study this tree effect, because we know that there could be some other event in galaxies. For example, I was pointed out 2 days ago that, of course, if there are merging of galaxies or some other effect like that, we can have a strong increase of vorticity, of course. And we confirm, and quantitatively, that vorticity is mainly produced in proximity of shock fronts and contacts. To end, I want just to thank Karl-Heinz for everything, and for his presence in Nordica. Thanks.
Thank you very much for this talk. I'm asking for questions, of course.
Again, my expectation would be that an important source of vorticity would be curved shocks, not plane or spherically symmetric shocks, right?
Yeah.
But to do this, you really need sufficiently high Mach number. And
yes.
So in real galaxies, it still can be that these expanding shock fronts produce more vorticity. What's your feeling about that? Because and plus there is a self-generation of vorticity, also another term. This curl of V cross on, right?
Yeah, but this induction term, it's called this way. Actually, in simulation, does not produce too much vorticity. So it's kind of in simulation, I've not observed induction or production of the dynamic production of vorticity. Regarding shock fronts, the problem is rather subtle because, of course, when you simulate, so speaking about medical simulations, when you simulate shock fronts, you need to some way solve the shock. So if we don't solve the shock, we don't add any subgrid model or something like that, we are not able to quantify. But in real galaxies, but my feeling is that, yeah, in shocks and shock fronts and contacts, especially when they are not parallel, oblique shock fronts and contacts, I think that that they are the main cause of vorticity, because it's a place in which the biggest amount of course, entropy is generated. But yeah, the point is that the range of Mach number is really different from the one that we have. So maybe what is needed is a study of shock. I mean, a study that is able to resolve shocks in some way.
Okay, maybe next question.
Yeah, I have a small comment. There was a paper by Barok-Merson-Glasner-Livni that they developed a linear theory of vorticity generation for compressible flow. And in principle, main conclusion from here is that it's not, you don't need to have high Mach number, it's enough because Mach number is only 1 in order to get strong generation of vorticity, and I think it's very nice to compare this analytical series with your simulations.
But indeed, we have a generation for Mach number that is slightly higher than 1. One is that I personally don't know when you go to Mach number like hundreds, this changed, because that's real change.
But Igor, I would guess that the paper you mean, it just extends, for example, the old results of covaginate. It's about the interaction of various perturbation modes in fluids, where, for example, interaction of sound and sound can give vorticity to some odd Mach number. So I would guess it's the extension of that. Here, the system is different.
No. Very similar. Very similar. Of course, here, dissipation processes are practically ignored. I mean, was ignored in analytical theory. But this is the first analytical theory of this effect, which really yields quantitative results. I think it will be very useful to compare.
Yeah, we don't know this reference actually, but indeed it would actually agree with our results because we find a plateau after Mach equals 1. The same as we find for shear and vorticity, there's a plateau when the shear parameter is 1 or when the Coriolis number is 1. So these are very plausible results now, I think.
But still, it would be important perhaps to compare these results with, there are lots of numerical estimates. For example, in the place where people do discuss vorticity generation in shock fronts is in the cosmological large-scale structure formation.
Yes.
And I can't remember now the references, but they have quite reasonable models, well, order of magnitude estimates at least, of vorticity generation in shocks which are inhomogeneous, in an inhomogeneous medium, where a shock encounters a dense cloud, for example. This is the place
there's
where
also a number of
generate.
There's also a number of numerical simulations which seem to show shock vorticity generation in isothermal flows where it shouldn't be possible. And it is clear that these are really just numerical problems with the code. If you use, for example, if the effective rate of strain tensor is not symmetric. So there's a recent example in the literature where the flash code was used and vorticity generation.
I do not want to interrupt this interesting discussion, but I think we should move on to keep in time.
And let's mark the end of the talk.
Hello. It's okay then. It's okay. There should be some problem with that. No, I mean, it's not a people. Yeah. Yeah, but this is the other one. Yeah, but this is the other one. Yeah, okay. I would like to thank...
Shall I announce?
Sorry.
So the second speaker of this morning session is Luis Garcia with the title Galactic Dynamo from Torsion Modes of Lorentz Violation.
Okay, thank you. I would like first to thank Axel and Nordita for the invitation. And, well, first of all, is this, let me talk a little bit about the title. This paper is more on the, for not exactly about dynamos, but is for galactic dynamo seeds, which are the the primordial fields that basically that happen on the electron-proton plasma, and there are subsequently amplified by this distortion mode. The word torsion here is a little bit different from the torsion that Professor Park had addressed yesterday. In his case, it's referring to a torsion of lines and magnetic field lines. Now here, the torsion is of the space-time. I mean, it's kind of, that terminology was taken from exactly solid-state theory, when you have dislocation of crystals. And then you may have torsion on the two-dimensional space, which is not the case of the torsion of Professor Park. So it's a little bit different just for the mathematical comprehension of the thing. Well, let's start doing this for the with the QED. In general, these primordial fields are investigated using QCD or quantum chromodynamics. But although QED is a little bit easier to handle, some specialists say that this QCD is better. So I tried to do it in QED in this kind of geometry. The reason why I work in the torsion space with Minkowski metric is first to make the things easier in terms of calculations. In second is that you can apply domain walls, because as you might know, domain walls in both sides of the walls there are flat space, and inside the wall is a bunch of spin polarized particles, which gave rise to this geometrical interpretation of torsion. So I used Lagrangian problem here. Lagrangian, which is this formula number 1 here. This Fij is the electromagnetic field tensor. The R star and quantities are the curvatures, and there are curvatures in this Riemannian-Cartan space. I mean, it's not only metric space, but also space with torsion. And then you can see from the formula 2 and 3 are derived from, I think I have the formula 2 and 3 are Maxwell's standard equations, anyway. And from this equation, I'll derive the relation between the magnetic fields. This formula 7 here is I use the axionic part of the contortion as derived from a scalar field. And that part on the left, yeah, okay, let me put it back. I have the formulas in a much simpler approximation. So this formula 15 and 16 are the formulas I would like to use. And I work in that gauge, formula 18. And then you have a wave equation from where in formula 19 and 20, where I should get the results. Formula 22 shows that I'm working in a flat space. And the solution is simple. One of the many solutions that you can find is for the vector potential is in expression 23. Okay. case, of course, the wave vector. Okay. All right. That's B's magnet field, finally here on 24. I'm doing several expansions here. Let me jump down. Okay, that's the main session of where I found the three-dimensional Maxwell generalized equations here from 30 to 33. As you can see, this the basic modifications is on Coulomb equation. So K is torsion. When torsion is constant, this equation reduced to Coulomb equation. And there are no monopoles, of course. And from these equations, you can derive 34. This equation, you can see that the presence of torsion and the variation of torsion makes that you may have an increase in the magnetic field component in time, which can be understood as the presence of what could be a dynamo effect. Okay. In the other paper recently, I showed some numerical computations of that. But torsion is computing. Now I forget to talk about what Lorentz violation, of course, is doing there. In the Lagrangian, we saw in the previous paper, the torsion, when the variation of torsion is constant, and you can see from the Lagrangian that the Lorentz symmetry is broken. Okay, that was where Lorentz violation is. Here, I use the same equations of the first paper. I'm not being able to pass the. This is stuck in the first page. Okay, I'll do it here. Okay. All right. Okay, these are pretty much the same equations, but yes. I use a specific form of the magnetic field. By the way, there is magnetic elasticity here with this choice of the magnetic field. And when you solve these equations, you find the following format for the contribution of torsion, which is this expression here, number 30. Okay. Let's enter that. Okay. This expression here gives you, this alpha is the fine structure constant. The K is the wave vector. K0 is a contortion term. And of course the ME square is the mass of the electron square. But from this formula, you can place limits for torsion or the Lorentz variation in two situations. First, for the galactic magnetic field on a scale of 10 kiloparsecs, which gave us formula 31. As you can see, the formula 31 is, as you can see, of course, this breaking is almost nothing. You can say that as far as galactic scales I consider, you can use general relativity without problem. And for the dynamo star data, like magnetars, I obtained, of course, a stronger broken for the Lorentz violation. Slightly stronger. Because of course this number is higher than the one we found out. And still, of course, very weak, but is in agreement. Of course, we can use also general relativity in dynamo stars. By the way, before I conclude, I would like to tell Karl-Heinz that I learned a lot about dynamo stars, seeing your papers on the subject in general relativistic stars. And I congratulate you for your birthday. Thank you.
Thank you very much. Are there any questions or comments?
Could you please point out what real object which so huge surface star magnetic field, 10 to the 14? If I remember correct, 10 to the 12 is some, how to say, limit after destroyed atoms. If maybe
yes, you're meaning the, if I understood properly your question.
Yes.
You're meaning this limit here, right?
Mm-hmm.
Okay, but I took it from some astrophysical books and data. Yeah.
Okay, but what is it? It's I don't know. How to say, neutron stars, you know. Maybe it's neutron stars. What is it actually?
The neutron stars.
Neutron stars.
Yeah, magnetar. Especially magnetar.
Okay.
I think for magnetars.
Any further questions? This does not seem to be the case, so let's thank the speaker again and move on in the schedule. So our next speaker is Axel Brandenburg with a talk titled Non-Local Transport.
Thank you, Martin. Thank you. You need to present. I really hate if people screw this up too tightly because it takes a long time. Right. This is a talk devoted and connected with work that is done together with Karl-Heinz. But it has and can have potentially broader significance. First of all, if we produce expensive three-dimensional simulations, we want to extract some understanding out of these three-dimensional simulations. And this is perhaps one of the reasons why it is good to make contact with other theories like mean-field theories that can describe the large-scale behavior of a system. If you, for example, generate a large-scale magnetic field, the comparison with mean-field theory is evident, and you want to substantiate such guesses. So that's the reason why there is an interest to obtain turbulent transport coefficients from simulations. There's the alpha effect that we know about. We have heard many talks about the test field method, and in this talk I will focus on the realization that the alpha effect is not just a number, it is actually an integral kernel. The same applies to turbulent diffusion. This is work together with Karl-Heinz and Martin Schwinner, our chairman, published in 2008, and there is a follow-up work on the non-locality in time rather than in space with Alex Hubbard, who's also in the audience. The test field method, remember, is can be applied to systems like the induction equation, passive scalar transport, and even the momentum equation. Even though the momentum equation is nonlinear, and how to deal with those cases, we have heard from Matthias Reinhardt the other day. But in the simple case of the induction equation, remember we have the original equation, the average equation, and the difference between these gives the equation for the fluctuations that is then solved not for the mean field that is obtained from this equation or this equation by averaging, but it is we solve this equation for an arbitrary set of different b bars, and that's how this equation then looks like. So b capital bar can take different forms, and this equation is solved together with a realistic representation, or with a given representation of the turbulent velocity and its mean flow. The standard case is to use, as we have also seen from the original work by Martin Schwinner, to use test fields that are either constant or linear. In order to obtain, if you do average over the x and y directions, then you have relevant components, relevant for dynamo questions, relevant components of the alpha and eta tensors that are where there are 4 different components: xx, xy, yx, and yy. The same for eta, where the k is the third index, which is always 3, because we can only differentiate such mean fields non-trivially in the z direction. If you insert now the first test field, we have the first component. The first test field is 1, 1. So we have 1, 1. And the first component, or the x component, gives us just alpha 1, 1, because the derivative of a constant test field must vanish. So that is easy. For the second one, in order to obtain eta t, we obviously need a non-constant test field. So then we take the second test field, b21, which has a constant gradient. And so therefore, we just get directly this number out of here, but we have an alpha of 1, 1 times z included here, which of course we have just obtained from the previous equation. So more formally written, this corresponds to writing down these 2 equations with the 2 unknowns, alpha 1, 1 and eta 1, 1, 3. So this is simply corresponds to inverting such a simple matrix. We will sometimes talk about eta with 2 indices that are related to the etas with 3 indices. The eta with 2 indices is what multiplies the current density. And remember, when the mean fields depend only on z, you can express all the possible derivatives of b bar in terms of components of j alone. So this is a special case, but it's I will use that case here for the rest. So when we tried this for the first time, then we obtained the following result. For alpha, and for the Roberts flow in particular, where there are analytic results. Roberts flow is independent of z. We obtained an alpha, which is constant, and had the correct value. But we obtained an eta t, which was not constant. So something was not kosher here. The reason is simply that the test fields are not compatible with the periodicity of the system. So therefore, we made a next attempt to use periodic test fields. Cosine z, sine z, and the same procedure applies. You have now a non-trivial component here, but again, inverting the relevant problem with the 2 unknowns is trivial, and you obtain the 2 unknowns alpha 1, 1 and eta 1, 1, 3 directly by inverting this this matrix here, which corresponds to this matrix. Is just a rotation matrix by accident. And now we obtain values that are constant. So the red lines are the new results. Eta t is now constant. This is a result for k equals 1. And here's a result for alpha. So you notice 2 different things. First of all, we obtain a plausible result in that the results are constant, as they must be. And secondly, they depend on k. If you change k even further, this is the wave number k here, normalized by kf, which we often use as the wave number of the energy carrying eddies. But for the Roberts flow, it is just the same as the square root of 2 times 1. So kx is equal to kf divided by square root of 1 is 2, which then gives 1. The results for alpha scale with either k, with this k. The larger the frequency of the test field, the smaller becomes the alpha effect. This is also plausible. If you take mean field theory and you expose it to a mean field that is actually not very mean, very smooth, but is actually rather fluctuating in space, you obtain a very inefficient response. And that is why the alpha must decrease with wave number k. This is plausible. But it also agrees with analytic theory that Karl-Heinz and Matthias Reinhardt and other collaborators worked out earlier already in connection with the Karlsruhe experiment. So according to that theory, both alpha and eta t have the form of a Lorentzian. First of all, there's a prefactor, which can be written as 1/3 times Rm times URMS. And this is under the second order correlation approximation, in which it's typical that all transport coefficients are proportional to Rm. They increase all the way to infinity. But of course, this is artificial, and it breaks down once Rm becomes comparable to unity, or even sometimes somewhat be less. But more importantly, both alpha and eta t depend on k in this form, which is known to astrophysicists as a Lorentzian. Lorentzian line profiles, for example, are well known. So this, the wave number dependence is Lorentzian. And this is a result under Soka, and this corresponds to this dashed or dotted line. And this is and the points, the symbols here, are the numerical results that you obtain with the test field method if you imitate Soka. So with the test field method, you can, of course, easily imitate Soka by simply neglecting these pain in the neck terms, the nonlinear terms. Then you obtain that same result, also for eta t, Lorentzian shape. In the case of the Roberts flow, the result is actually different if you go away from Soka in its qualitative shape. You still obtain something like eta k, but it becomes more shallow. And for eta t, you even obtain negative values for small values of k. But they are still small compared to the reference value that you would reach asymptotically if you had a fast dynamo, or so this is what we use for normalization, and it makes more sense in the turbulent case that I will come to in a moment. So it is still a small value which is negative, but it disagrees with the Soka result. This is for the Roberts flow. So there is a k-dependence, and the k-dependence is obtained compatible with the numerical results, or with the analytic results of Karl-Heinz's. But what else can we learn from this? This is really just the meaning that the alpha effect is damped for shorter wavelengths. No, the whole thing is more general, and it's actually entirely compatible with what we should have remembered all along from mean field theory. Go back to this very old work that Karl-Heinz presented at the IAU symposium in Czechoslovakia in 1975, where he already emphasized that the electromotive force should be written as a convolution integral with the kernel and over the mean field. And this is a convolution in space and in time. Then remember further that a convolution, at least for a homogeneous system, corresponds simply just to a multiplication in wave number space. So if you can write the electromotive force as a convolution, and here it's the kernel split into the two relevant components, or the two physically separate components, alpha and eta, this you can write as a multiplication in wave number space, where the Fourier transform is simply just the integral over, it's simply just a cosine transform, because alpha is symmetric in wave number, or in zeta in space. Same as zeta. So now we apply the same method to turbulence. It's a turbulent flow which is driven at a certain wave number kf, and so again we normalize our k dependence by kf, and we obtain data points. So we do a calculation for different, here we are showing two different symbols. One where we force at a wave number of 5 relative to the wave number of the system, and in another case at the wave number of 10. In both cases, once we normalize in this appropriate fashion, we obtain symbols that roughly lie on the Lorentzian profile again. At least within the range of wave numbers that we have considered here, which go all the way to, or go only to approximately 2, and in a few cases a bit further. So what does that mean then? Now we have to Fourier transform this, but Fourier transforming such numerical data is a difficult business, and it's much better to Fourier transform this fit, this Lorentzian fit. The Fourier transform of this Lorentzian fit corresponds to an exponential. And again, here are shown the symbols which agree very well with the expected result. So we now know, and perhaps, at least as far as we are concerned, we haven't seen that elsewhere in the literature, for the first time in that sense, we obtain the form of the integral kernel as an approximately exponential. The same type of the kernel has also been obtained for other cases. Here's, for example, the case of shear flows, or helical flows, and here's a result for shear flows. In all cases, the data fit very well with the Lorentzian shape. So, in that sense, we would find it now compulsory to regard alpha really always as a kernel, which is clearly relevant once you are talking about variations of the mean field that become comparable to the length scale of the energy carrying motions. Consider the case of the Sun. The wave number, or the length scale of the eddies is approximately 50 megameters at the bottom of the convection zone. And if anybody presents a mean field model which shows local variations of less than 50 megameters, clearly one has violated what we now know from the literature already, that alpha and eta are kernels. At larger wave numbers, we have not confirmed the same dependence yet, but there are theoretical reasons why the alpha might actually decay in a somewhat shallower fashion. By simple arguments with a Smagorinsky closure model, you would expect instead a k to the minus 4/3 scaling, which has not been confirmed yet. These results are rather similar to what already Dmitry Sokolov and I have obtained using not the test field method, but a much more rough method back in those days, where we really just used the actual magnetic field from the simulation and obtained alpha by fitting it to the and calculating moments by multiplying with the corresponding expected results. So we obtained, in that case, already a non-local dependence or a decreased response for higher wave numbers. Non-locality must also apply in time, where we have seen from Karl-Heinz's earlier work already that alpha is really also a convolution in time, which corresponds to a wave number dependence. We have calculated the test for time-varying test fields that are oscillatory in time, alpha and eta t, and they typically have a real part and an imaginary part. The real part is first constant for small wave numbers, that corresponds to the value that we all normally use if we ignore time, or this time dependence or memory effect. So there is a certain value for small wave numbers, and of course there is a decrease for higher wave numbers, and a somewhat shallower decrease for the imaginary part, which decreases like omega to the minus 1, whereas this one decays like omega to the minus 2. This can have important effects in certain cases. Compare, for example, the growth rate that you obtain by numerically solving the Roberts flow. And compare that result with what you would expect from the dispersion relation. The dispersion relation should give you an alpha, should give you a growth rate which is equal to alpha times wave number minus the total eta times wave number squared. You insert these values that you normally obtain with the test field method, and you find disagreement. This is the result from the dispersion relation. But this disagreement can be quite extreme. But why is there such a disagreement? The reason is, of course, that we have calculated alpha and eta for the time-independent case. And of course, that's not correct, because clearly we are making always the assumption of homogeneity and time-independent stationarity, and then we are looking what is the rate at which the mean field increases. If it increases, it's no longer stationary, of course. So clearly we have done a mistake, and this mistake becomes quite evident here. So what we should do instead is calculate alpha for a time-dependent or for a growing mean field. For example, one where for a field that grows exponentially with the growth rate s. This is, of course, just the Laplace transform, which is a more relevant transform to use in this case. But of course, s is really just the imaginary part of omega if you consider complex frequencies. And if you do this, you obtain values now for alpha and eta, which are s-dependent. Therefore, you obtain a lambda that is s-dependent. And of course, the relevant values that you want to obtain are those where lambda is equal to s, which means lambda lies on the points on the diagonal are to be looked at. So this corresponds for this Reynolds number of 50, which is shown here, to this value of 0.11, which agrees perfectly now with the numerically obtained growth rate from the direct simulations. So you see the test field method is not only accurate, but it even forces you to abandon the simple assumption that the alpha kernel is really just a delta function. There's even more practical relevance because, as Piali showed you, we can obtain the turbulent transport coefficients from for cases like the magnetic buoyancy instability, which is a case where there's no flow whatsoever if there's no magnetic field. So it's, in that sense, an entirely nonlinear case. And nevertheless, the quasi-kinematic test field method works. But in order to demonstrate this, you want to demonstrate that the original electromotive force is reconstructed with the numerically obtained or test field wise obtained values for alpha and eta. And here you see to what extent this result agrees if she goes all the way to wave numbers of 16. So you obtain reproduce this negative part here, you obtain the positive part here, and you obtain the sign reversal here again, which you cannot reproduce at all if you just use the basic mode. And I think that is the method. That's the relevance of this method. It is really important nowadays. And I think I'm finished. And so with this, I think we should be grateful to Karl-Heinz for having come up with this test field method, which really was only in the last 5 years that it has been devised and numerically established by the work with Karl-Heinz and our chairman. And it's nowadays a method that is used almost routinely, or really routinely, in many different applications. Whenever we have a result for turbulence, we can routinely just invoke the test field method, obtain results for alpha and eta, and see whether we can understand these numerical three-dimensional results in this way, using mean field approach. Thank you.
Thank you very much. I imagine that there are maybe a number of questions or comments. Oh, yeah.
Axel, how about this green function method? Usually, causality has to be preserved. So the time evolution is preserved at the price of selecting only particular bases in the reconstruction of the green function. Otherwise, you might get easily non-causal behavior, something which is real physical.
Causality means the following. You can calculate for a monochromatic wave, the response, and in that case it really just corresponds to a shift in time. And you can then formulate the question as to say, the EMF that I obtain now is a result of a mean field at an earlier time. And so this is described by a relevant phase shift, which exactly, yes. So that's, and here's a numerically obtained result. So as long as this phase shift is positive, the results are causally causal. So numerically it's obtained. It does not, however, have to come out this way. For numerical reasons, for example, it might deviate, but in this case, in the result, in the case of turbulence, it actually does agree.
It's just a comment. You were discussing the Roberts dynamo, and it's a very special dynamo. Being steady and two-dimensional, you get very curious structures. Well, not curious. It's very structured in the large magnetic Reynolds number limit.
Yes.
And one of the features is you basically expel all the flux from the centre of the eddies,
yes.
all the fields in ropes.
Yes.
And so the type of calculation to work out what goes on there is rather different to those calculations that are normally done in near field electrodynamics. And Steve Childress was the first to investigate these boundary layers, and he got an alpha effect from that, which was quite large, based on the fact that everything's in these sheets. These are really comments. The nice thing about that dynamo is you can sort of talk about a generalized alpha effect. You can just talk, it's basically like a growth rate, and you can make it a function of the wave number, the axial wave number. As the Reynolds number goes up, these sheets form ropes. Essentially, they're very. You've got alpha minus.
What are you getting at? What are you getting at?
Well, the issue of the growth rates. The growth rates.
Yeah. Okay.
Okay, that's where I'm getting to.
Of course, yeah. So let me then.
Can I just finish what I'm going to say? You commented on the growth rates. I did this years ago. You put the fact that the field is growing into the calculation, and then you can find out that there are growth rates very fast to the convection timescale, but not quite.
Yes, so my comment is the following. The Roberts flow is extremely special. I fully agree with you. The only reason why we sometimes use the Roberts flow is because there we have numerical results available. Analytical results available. And the test field method is supposed to agree with this to all relevant digits. So we have here...
It can't work. I mean, the alpha, Frank made this point. You have basically an alpha effect, which is a function of k. To understand what's going on, you need to know that whole function. Mean field electrodynamics just is a Taylor series expansion of that quantity.
Taylor expansion
in wave number. But it's based on the fact that the wave number is small. So it's a Taylor series expansion of. It's a really nice problem because you can actually get a complete understanding of the whole dependence on wave number. And mean field electrodynamics is associated with this Taylor series expansion in small k.
Yeah, but we take, of course, all k's into account.
Not when you've got there an expansion of k and k squared. You've taken the first two terms.
What do you mean? I showed
well, I can see it on the sheet.
Omega. Here we have the entire k dependence and all these plots.
But the objective is to get the first two terms.
By the way, that's no longer Roberts flow. So I should emphasize again. The Roberts flow is one example where we have exact results. The test field method agrees to all relevant digits, and that validates our method. And it's important because the method is not that easy. You want to make sure there is no numerical bugs in it. And so it's great that we have an analytic result against we can compare. And once we have validated the method, we can use it for results which nobody else has ever looked at. Turbulence. Turbulence with shear. Turbulence with stratification. All these different cases. For the first time now. Using a method that has been validated to 3 relevant digits.
Okay, Axel, I think you made the point.
Last question, I think. What product of omega naught and tau for time-dependent alpha?
So omega, tau is approximately 1/10 time.
So it means that it puts possibly a change sign of alpha here, potentially.
It does.
Exactly.
I showed that only one result, I think. You are referring to the yes, here, of course. So a better fit to these results, a better fit to these numerical data is this functional form, which corresponds to an exponential multiplied by cosine. So yes, there is a reversal of sign.
We have time for one more question.
It is just a suggestion. I highly appreciate the worry of Andrew, but we checked with Nathan and Pickering and some others that if you there is a method how to overcome this worry, it is sufficient to introduce noise in the parameters of the Klein-Roberts flow, and it radically simplifies the situation and makes it is a way how to overcome the worry.
Karl-Heinz has a comment. I think we should hear what he says.
I have only a historical remark. If you mention the test field method, you mention Martin Schwimmer, which is completely okay, and you also kind of mentioned also my name. But it was Matthias and I who cooperated with Martin, and I think the most clear idea of ours came from Matthias.
Who is in the audience, yes.
Okay.
Thank you.
So, thanks Axel again for this nice talk.
Am I audible, please?
So, the last talk of this morning session is by Kumashiwa-Malapaka, a study of magnetic velocity and forced and decaying 3D MHD turbulence.
These are, by the way, the highway. It should be on, right?
Hello? Good morning, all of you, and thank you for the organizers for this nice opportunity. I am currently working as a postdoc in JLL, Jacques Louis Lyon's lab in Paris, on a ITER problem. But for my PhD at Max Planck for plasma physics, this was my thesis title, A Study of Magnetic Helicity in Forced and Decaying 3D MHD Turbulence. And the overview of my talk is that I would just give a brief run-through of MHD magnetic helicity, as I don't need to introduce MHD turbulence here to any one of you. And then I would start with what my equations are, the way I write the equations and the simulation setup. Then go through the spectral and structural analysis and give a final summary and conclusion. Now, this is my first time that I'm in front of an audience to whom I need not explain what is magnetic helicity and its properties. And I'm very lucky, I feel. So I want to point out to other point that I would try by the end of the talk that probably it is possible to explain or it might be possible to explain large-scale structures like these. This is a radio blob or radio halo seen in the cluster of galaxies observed through GMRT at 621 megahertz, and it's a paper in 2009. And actually, this helped me to understand my own work, and probably I have some applications to the astrophysics. Because initially I thought my work is only numerical simulations, then I understood that possibly there are some applications to my work too. No. A historic overview. Say magnetic inverse cascade of magnetic helicity, that is the spectral the transfer of spectral flux from small scales to large scales was first observed in the numerical simulations of EDQNM theory, that is a closure theory, in 1976 in the paper
Bouquet et al. And you clearly see that they force at very small scales here, and they and see the growth of magnetic helicity spectrum into larger and larger scales. These kind of huge, say, decade of spectral, say, difference between the small scales and the large scales was never obtained. The best I could see previously was of Brandenburg's work in 2001 APJ paper, where he does not represent magnetic helicity, but magnetic energy, which would scale 1 power less. Sorry, I forgot that they may also, in this paper they also mention that the power law for magnetic helicity would be k power minus 2. And for magnetic energy, it would be k power minus 1. And in this work of Brandenburg, he shows that it is in fact k power minus 1, and there is this transfer to larger and larger scales. But the way, my motivation was to obtain this kind of large scale separations. So this motivated to start our work, and the way we write our equations is shown here. We take the single fluid approximation, incompressibility, no gravitation, no rotation, into and no relativity effects, and we write these equations in, say, non-dimensional form, where now B becomes B is in the units of alpha and velocity, and important parameters in this equation are these. That is, the hyperviscous diffusion coefficients mu n and eta n, and further Fv and Fb are the forcing terms for vorticity equation and the induction equation respectively. And in order to avoid boundary effects and back reactions, I use the energy sink which would only act in the small k or large scales. And as usual, I take I see that there are no monopoles in the equation, and I also see that there is no rotation. That's why the del V is also 0. Now, just to point out that if n is equal to 1, these parameters would represent the inverse of Reynolds number and magnetic Reynolds number. Their ratio, the magnetic Prandtl number, I put it as 1, and the Reynolds numbers would depend on the characteristic length scale and velocity to kinematic viscosity and magnetic diffusivity as shown. Now, what is the purpose? And if I put Fv, Fb and alpha to 0, this system of equations would represent the decaying case. Now, what is the purpose of the whole exercise? The purpose of whole exercise is to obtain spectra like this, which have 3 distinct ranges: say the dissipative range, the inertial range, and the drive range. But to make it very clear, my driving never sits here. It will be either here or somewhere here in the decay case. Next, the simulation setup. I use direct numerical simulations to solve the set of equations shown above, and I use a regular cubic grid with a resolution n cube, n being 1024 in my case. I use periodic boundary conditions and a standard pseudospectral method where wherever there is a convolution, I go back into the real space, multiply, and come back into the Fourier space. And to overcome, say, the de-aliasing effects, we use spherical truncation in the very large, and we see that if you use spherical truncation, it would cut down the number of calculations by 2/3 less than the 3/2 aliasing method, and the error is of the order of numerical error, so we can discard that. And as I already mentioned, we use hyperviscosity. And in this work, the initial conditions are random phases and fluctuations of Gaussian, which are peaked in intermediate K for decaying turbulence and very large K for forced turbulence. And the forcing Fv and Fb are over a band of wave numbers around the initial condition. They are random, delta correlated in time, and add a fraction of say for say kinetic helicity, like the term Fv adds kinetic helicity into the system, and Fb adds magnetic helicity into the system. And we can control the amount of magnetic percentage of magnetic helicity or kinetic helicity put into the system in the forcing system, through the forcing term, apart from the initial conditions. Now, coming to the results, my initial condition, as I mentioned already, is here in the at the wave numbers around 200 it peaks at around 206, and my forcing wave numbers are between 203 to 209, and over time I clearly see the peak of magnetic helicity moving to larger and larger scales or smaller and smaller k, and this is a clear inverse cascade. And you also see that the separation of the scales is at least a little more than a decade. Now, until yesterday, I would have claimed that we saw a strong power law behavior, but after discussions with Professor Ulrich Frisch, we say that probably we are going towards it, asymptotically towards this particular point, towards this power law, but we cannot strictly claim a power law behavior, as our resolution probably does not allow us to do so. But the interesting aspect is that we see a constant flux. That is, the inverse cascade flux, that is, if you take a shell and the flux is flowing into the shell, that is plotted, that is taken as negative, and is the negative of negative is plotted in this particular magenta color, and if the flux is going out of the system, it is plotted in blue here. So you see that a large amount of flux travels to the small k values. Now coming to the decaying case, a similar thing is seen here. The initial condition is set at k equal to 70, and you see that the magnetic helicity moves into the smaller and smaller scales. But can you say this is cascade? Probably not, because it is having so that the flux of the magnetic helicity in this particular case is not constant. So probably it is only a inverse spectral transfer and not a cascade. But here in the decaying case, I can clearly say that there is a power law behavior which is of the order of k power minus 3.6. Now, the important point from the previous slide and this one is that the predicted k power minus 2 behavior from the previous works is not seen. Now, if we go to the energies, how they are present in these works, in this particular work, I start with equal amount of magnetic and kinetic energies here, and you see that in the large k values, the magnetic and kinetic energies are almost equipartition. But as you go towards smaller k or larger scales, the magnetic energy dominates the kinetic energy by almost a factor of say 10 here, as can be seen here. And here too, the flux of energy, if you see, it is totally going, it's not a cascade, but a total energy that is plotted here is not a cascade, but a spectral transfer only. Now, what is the nature of this particular cascade, or what is the particular nature of the interactions that are taking place? This was a work done by my colleague Yasser Rama. He used Kreishnan's Q functions, which simply put are some kind of probability density functions, which would give in a simple manner. That is, if the peak of this density function peaks around 0, the function is highly non-local, and if it peaks or close to 1, it is highly local. And it is his work I am presenting here to support my work, and but the data is mine. And you see here that magnetic helicity is the only quantity that is having highly non-local behavior, whereas all other quantities here, that is magnetic energy, kinetic energy, and kinetic helicity, all other quantities are highly local. And it's the same for the decaying case too. So with this say support in my hand, I'm trying to interpret my results. I use the EDQNM equation for magnetic helicity, which is shown here, where the terms transfer, say, interaction terms between the two fields, these three terms are shown here. And theta kpq is a characteristic eddy damping time of the nonlinear energy flux involving the triad kpq. And if we look at these terms individually, the first term would look as shown here, and the second term would look like this. I am not representing the third term for a specific reason. Say now we simplify out, say, all this term to look at what actually it means. The first term would mean that it would represent the advection of magnetic field fluctuations in the turbulence. And second term would represent the twist of the magnetic field lines in the field. And third term would be an interaction within the interaction of magnetic field within itself through the Lorentz force term, probably. So, but using the argument of Keith Moffat, which says that inverse cascade is a process which involves both magnetic field and kinetic field, we ignore this term and equate these two terms to understand the spectral dynamics between the kinetic helicity and the magnetic helicity. I'm missing an M here, sorry. There should be an M here. And if you equate simply by, if you just equate these two terms now, to understand the spectral dynamics between the two helicities, the equation can be written in this form, or even better, in a form shown here, which say Rk, a function that can be plotted. So we then do the same. We plot this function here and see that it does not really go in a constant manner. So which we expected. Then Wolf came with the explanation for this. He said, see, we are not actually looking at the kinetic helicity and magnetic helicity the way we should be looking at. Dimensionally, they can be represented this way, KEV and K power minus 1 EM. And so if we include the dimensionality into the picture and then take the spectral dynamics form, you would end up with a square term to the this particular term, and the rest of the terms remain the same. So now if we plot this second function, that is with a square, you see that it agrees to a certain extent, it's almost flat to a certain extent, and also goes and also shows almost parallel to the compensated line, here. And in the decaying case, it's almost flat. So probably now we can say that this is an interesting relation which represents the interaction of magnetic helicity and kinetic helicity in the spectral dynamics, which is, say, allowing us to understand the structure formation and also several other behaviors. I should also point out that in this particular equation, we saw power law behaviors for magnetic energy and also kinetic helicity. The only quantity which did not show any power law behavior is kinetic energy, which is as expected. But the new thing is that kinetic helicity scales with a k power minus 0.4 power law. Now, until now I have not uttered the word alpha, but now I am trying to go there. Now, what is the relation of that particular work and the alpha effect? If you write alpha as a difference between current helicity and kinetic helicity, we know that current helicity is k square Hn. So if now, as I already argued probably, and current helicity, this particular relation between Hk and Hm should have that additional term. Oops. So then the alpha would have read like this. And 2 days back I learned that this is the same behavior that Axel Brandenburg and Mattia Reinhardt are seeing in their work. That is, they are seeing a b power minus 4, and this term can represent the quenching of the alpha. So this is the relevance I am finding after I came here to this meeting. And thank you, Karl-Heinz and Axel, for this. Now, visualization of the structures. This is the three-dimensional isosurfaces of the magnetic field shown here for the entire 1024 cube. But now, the way I want to represent them is like this. In the first case, I take a cut across the field and show you. If you can see them, in the first case, you really don't see a nice structures that we are used to see, like as in the decaying case. And these are filtered case. This is a filtered case. Actually, if I show you the original one, it will be even worse. So the isosurfaces are shown here, and isosurfaces of the magnetic field for the magnet in the decaying case are shown here. They are really like flux ropes, whereas here you see that it is not so. But then I was not satisfied. I was always thinking that force case should always give last case structures. But when I did not find, I was worried. Then I stopped the forcing after it reached this state. And immediately the large scale structure started appearing. Similarly, if I stop at a much earlier stage in the system, I'm getting a different kind of magnetic field structures. So, what does it tell me? It tells me that probably in some astrophysical scenario, like the one I mentioned earlier, that is, say, the cluster of galaxies, where the central engine is now switched off, but it supplied the helical field, like jet or something, into the plasma far off for some time. Then, and no more there is, say, the central engine on, then the plasma at a farther distance would have become energized and also turbulent and started decaying and is forming the large scale structures which we are seeing. And the forcing, the amount of forcing that is going into the system will influence the size of the structures. This is the idea. And if you see how these things develop, you see that if from the initial state where I remove the forcing, slowly in time the large scale structures develop. That is these structures. Now the important aspect is to look at the structures, look at these points. These are clearly the reconnection regions. And if you can see here, the number of reconnection regions in this particular view graph, are far larger, whereas in this particular view graph, they are few. So there is one more important point I wanted to make. The point is that reconnection and inverse cascade appear to go in the, appear to have some relation, which I am not yet clear. But I am seeing that if the inverse cascade moves to larger and larger scales and forms larger and larger structures, fewer and fewer reconnection regions remain in the field. So there is a symbiotic relation between these two, but it is not yet clearly understood. Further, I did ESS and then fitted the curves with the Shilevek model for the structure functions in the case shown for this particular case. And I see that in the initial forced case, the codimension of the structures satisfies a Kolmogorov type function which has a codimension of 1.5, that is a fractal dimension. Whereas if I remove the forcing, just remove the forcing and plot the data moves onto the decaying, that is the decaying case, moves to the Kolmogorov type structures which have two-dimensional features. So there is a shift of dimensionality of the structures, which I already pointed out through the filtering process, in the when you force the system or when you just allow the system to decay. Further, I plotted correlation lengths. I calculated correlation lengths for the system, for this particular system shown here, that is the time evolution of the magnetic field, and at these 4 points, and also looked at the magnetic dissipation at the same points and plotted them one against each other. The correlation function, and then calculated the correlation length as a fit that whenever the correlation function falls to 1 by e, I take it as a correlation length. 1 by e being exponential. And I see that as correlation length increases, the magnetic dissipation decreases. So there can be a state where magnetic dissipation totally goes to zero here. Ignore the part here because the extrapolation fit just went through the zero line. But it's up to here that we need to concentrate. And here you see that theoretically it is possible that the structures can grow to a size where they stop dissipating any further. Or probably this is the forced free state which people talk about, which I am not yet clear, but I believe so. And so these are the important conclusions I can make, that say inverse cascade of magnetic helicity from small scales to large scales is observed in both forced and decaying, whereas I should say at least say spectral transfer. And then magnetic helicity transfer is highly non-local. And using EDQNM, we found a new relation and dimensional analysis, which could also be related to alpha quenching here. And the large scale magnetic structures might be a result of both forced as well as decaying. Both are needed to form large scale structures. And intermittency models change. And finally, I don't know whether I'm getting there, but I feel that I'm getting towards the force-free field of the magnetic field. Thank you very much.
Thank you very much. Are there questions? Working? Yeah. Yeah, it's not a question. It's a comment. Around 1975, with, who was it, Ali Pouquet, Jacques Leroy, such people, using the methodology introduced by Kragman of absolute equilibria, the one he had used to predict inverse cascades in two-dimensional hydrodynamics, we predicted an inverse cascade of magnetic helicity in 3 dimensions. Most of you know. In 1981, actually it was 1980, it was published in 1981, we did what was at that time state-of-the-art simulation on the NCAR machine. I think they were 64 cubed MHD, which did show a dynamo effect, and when we had helical forcing, we observed something that qualitatively resembles an inverse cascade at a very qualitative level. But it was far from what one would have predicted using Kolmorov-Krajnan type arguments, maybe dimensional arguments. Dimensional arguments, when you look for a helicity, magnetic helicity spectrum, and with a given helicity injection rate, and then you try to relate this with the wave number dimension, analysis tells you that the only possible choice is k-2. Yeah. But that implicitly assumes that this cascade is local, because if it were non-local, other ingredients could come into this game, and then it's undetermined. In 81, we saw some indication that things are non-local, and that they can perhaps be described by an approach suggested by, again, Robert Krajnan. In 1979, a paper at which Shiva and I looked last night, which is one of the many mechanisms one can think of where the alpha effect is reduced by the action of a large-scale magnetic field. Then, if things are non-local, of course, one can have all kinds of possibilities. Interestingly, non-localness doesn't make things more complicated. It makes things simpler, because you can then use multi-scale methods, and there's some hope of doing theory. Now, I haven't just listened to Shiva now, I also talked to him for a number of hours, and I'm not convinced that he's wrong. Of course, the high K range between the forcing and the maximum wave number is really short, etc. But I think the general idea is right. But I realized something during your talk now, is that we have now a new case of where we have to warn people against the use of closure. You see, when you apply closure to this kind of MHD turbulence, you do find a local cascade. But there is a mechanism which is destroyed by closure. Let me tell you what it is. It's what people generally refer to as depletion. Reduction of nonlinearity, which becomes much, much weaker than dimensional analysis would predict. And it's just, for example, when you align curl B with B, as you unavoidably do when the large-scale field is driven by an alpha effect, then it becomes a leading order force field. Now, this kind of alignment, which is not taking place in a fixed direction, but in a random direction, is not captured by closure, but would have to include at least fourth order moment to capture it. And what I have known for many years is that this failure to capture depletion is the reason why closure, when applied to two-dimensional MHD, predicts finite time blow-up. But when you do a clean, high-resolution simulation, you don't see any evidence for it, and it is due to that. But here we have some, but singularities have to do with high-K behavior, small scale. Here we have something at the opposite end. And I believe that the mechanisms which make this non-local is this depletion, but now it's a large-scale depletion, because the magnetic field cannot self-interact easily. In the real world, in the closure, yes. So it's an interesting situation.
Thank you very much for your interesting comment, but I guess there are maybe further questions and comments.
Yeah, a very remarkable talk and story in that because you find a real cascade with a constant flux of energy, and the reason why I have been thinking that it's not a cascade is because I've been looking at the saturated case when the condensate has already formed. So in your case now I see quite clearly that you do have a real cascade as long as it hasn't reached the scale of the domain yet. Regarding the K to the minus 3.3 spectrum that you find, the only other case, I mean, in our simulations it looked like minus 2 for the magnetic helicity, and minus 1 for the energy. The only other case that I know of is a case where Kandaswamy Subramanian and myself solved the equations for the correlation functions with helicity. And in that case, we can go back to, which is in real space, in that case we can go into Fourier space, and we do find a K to the minus 2 for the energy, and therefore minus 3 for the magnetic helicity, which I was always very, very puzzled about. So now I believe maybe that might even be right. Very interesting.
Are there further questions or comments? So let's thank the speaker again and close the session.